Tala, good morning. Good morning to you all. Lama ya hinoda. Hinoda kati. Hello.
Good morning, sir.
Good morning. Tala, good morning. I hope today Zoom session may be more clearer to you because signals are quite stable. In any case, if power goes off, suddenly this Zoom will be stopped and I will reconnect with another Wi-Fi source. Yeah. Till then, this is no issue unless there are power interruptions. Yeah, I believe you can remember this example we have done last week. A little more things to do here. A little more things to do here. Example, something like we can come until the work done, calculations. So we need to learn until this level today. So the best is still the best is the balloon example because it's easy for you. That's why. So this one is with the focus of evaluating the work done in the closed systems mostly. So if I go through this today, yeah. So as you remember, we looked into the sun, balloon, clock, and the ground. Yeah. So this is the same thing here. So let me look into this again. So I put here little extra things. You can see the dash line here. This dash line, I represent the boundary, system boundary. Okay, system boundary. So dash line is really shows the limits of the space of the system. Here the system means the inside the balloon the air contains. The air contains. So even the rubber balloon, the rubber surface is outside the system. So rubber surface is also outside the system. If you look into item, the state 5 and state 6 may be clearly showing it. State 6, you can see the dash line. So dash line is the surface of boundary of the system and it's totally containing this air trapped in the balloon. Okay, so this is to understand system boundary as well. Okay, so I will add the keyword here, system boundary. Okay, system boundary. Also here, added. Okay, for today. For today discussion, system boundary also added. So if you look into example, let's say piston cylinder system. Piston cylinder system. So you can draw there. So let me try to draw here the cylinder and a piston. Let me draw the cylinder first. And if I do the piston, let's say this is the piston. So if this is the piston, okay, if this is the piston, so now we can identify the system. So let's say the system, if I put in a dashed line, it is something can you see the dashed line? Yeah. So dashed line is the boundary. So boundary, system boundary. So within the boundary, you will see the closed system. That is what it is seem like. The balloon. It seems like the balloon. Okay, no difference. It seems like the balloon. Okay, so that is important. So you can see this balloon. So different sizes. Okay, you can see the expansion. Okay, boundary. So you can see the expansions here. Give me a second, Buddha. Give me a second. So here you can see the volume increase in the balloon system. Okay, same way as the volume increase with the in the balloon example, you can see somehow the pressure, yeah, pressure and volume. So you have the understanding from the previous diagram. Okay, pressure and volume. So here also in this case, so let me draw. So initially the piston can be up, let's say piston can be up, then piston expands, okay, and there can be some more expansions, so you can see like this, okay. In the balloon example also you can see the expansion of the boundary, okay. So when you experience the expansion, so you can see the volume increase and also there can be pressure changes as well, okay. There can be pressure changes as well. So I take the two cases now. One is the balloon case, the other is the piston cylinder system, okay. Yeah, so today you are going to understand this to the fullest. So I would say once you understand this, it is almost done. It is almost done. The knowledge of closed systems. So for this case, let's say for the expansion of this cylinder piston system, so you can see that during the expansion here you can see some three instances. The volume is increasing the volume is increasing, the temperature can be getting changed, maybe, yeah. Pressure, there can be a change as well. Okay, state 3. Okay, state 3. So here let's say the triggering of this expansion, state 1. Okay, state 1, triggering of the expansion, maybe because of the fire. Okay, maybe because of a fire. Because of a fire, so let me put, fire means a spark. Okay, immediately with the spark, there may be a pressure rise, and because of that, the boundary moves. Okay, so let me type a bit here. State 1, pressure rises because of the spark or fire or firing of the fuel. Okay, firing of the fuel. So inside there can be fuel, petrol or diesel, whatever, or gas types. So once fired, pressure rises. Okay, it is almost sudden. Let's say suddenly rises. Fuel. And the piston starts moving, means system boundary expands, or in other words we say the system starts to do a work, expansion. Okay, piston moves means the boundary expansion. You can see initially the boundary size, here now the boundaries increase, expanding. This is again further expanding. So state 1, state 2, state 3. So let's say instead of 3, I will take state 2 here. So this is state intermediate. Okay, intermediate state. So state 1, state S. Let's say state S is here. PVTM. Okay, state 1, state 2, and state S. Okay. So this boundary, you can notice that boundary expands. Means moving boundary. Okay, boundary expands means moving boundary. Work is being done. Okay, work is being done. No, work is done. Or work is being performed by the system, or the system performs work. So system is doing a work. Okay, more simple way. Okay, so I believe you have to have this little understanding. Same way for the balloon, there is no fire, but okay, there is no fire, but slowly receiving of heat. Okay, slowly receiving of heat. Okay, slowly receiving of heat. Okay, you leisurely try to understand this, Putana. This is one-time learning for you. Okay, one-time learning. Yeah. So it is okay to be patient. So slowly receiving of heat. See, same like fire, of course. But in the system expansion, it receives at state 1. Okay, state 1. And the work done from 1 to 2. But receives at state 1 true. But there can be heat lakes. Okay. Here no heat addition, but there can be heat lakes. So here you have a very significant fire here, but there can be heat leaks during 1 to 2. Okay, 1 to 2 there can be heat leaks. Okay, there can be heat leaks. So there can be heat leaks. I put it in red color, the heat leaks. So that's why even though this Q is here, the heat is here. So same way I will put for the balloon, sorry, for the balloon also there can be states. So state 1, okay, and state S, I just put same here. State 2, this way. Of course, if you need further details, you can look into the notes, because I have already passed you a very good note for you to understand. These notes are very relevant and it's going well smooth and well meshed with your syllabus. Step by step knowledge is there in the notes I have already passed to you. Good to have a printout of that. And these lectures are only supplementary to understand those notes. Okay, Butala? Only supplementary. Today we can see only 39 students. I don't know why today. Anything? Can one of you respond? Why only 39? Kenval and Mughal 39 students. Rahim, Puta, can you explain why only 39 students? Yes. Why only 39 students? I think you better communicate with the students, your batchmates, and ask them to join the lectures regularly. That is very important because during the Zoom sessions, you are learning something with better thought process. So you, the class, and myself as a lecturer, we are thinking on the same line here. So it may be helpful. So some thoughts are there, some acceptance, some questions, some understandings, even some ideas are being taken place when you join the discussions. Okay, so you can get the things clarified as well. Okay, so it is very important to join the class. So let's say the heat. Okay, heat received from 1 to 2 as Q1, 2. Q12 I put into the general state here. Okay, Q12 I will put generally this is Q12 heat. Sorry, heat Q12. See, from state 1 to state 2, everything heat Q12. So the same way by right. Okay, so let me do a new slide for this. For this case also, in more general way, of course there is an initial fire and there can be heat leaks because you know in motorbikes even there are fins to dissipate some extra heat. Some vehicles there are radiators uh, with working fluid such as a coolant. So you can see throughout the process there can be heat leaks as well. So that's why the net heat, let's say even for this power stroke of this piston cylinder, because the stroke means this expands, so this stroke, so you can see this produce some work. So your Q12 is here. Okay, your Q12 is here. I hope you can understand. So it's the same thing here. Q12, 1 to state 1 to state 2, we call it 1 to 2. Okay, state S, this is general state. State 2. Okay, this is general state. So state 1 is the initial here. Okay, no matter the balloon or its piston cylinder system, so you may have the same. Okay, you may have the same. So boundary expansion work done. For this case, these two cases, you can see because of the boundary expansion, if you think of a work done, it is from the system for sure. This work done is from the system. Okay, from the system. There is a work done because of the expansion. Okay, but if I follow the sign convention, this W12, okay, let me put it here. Yeah, first, Q12 is okay for you. You want to get little space for Q1. And you may consider a work done by the system W1 to 2. This is state 1, this is state 2. Work done during state 1 to 2. Okay? Same way, even in the balloon expansion, you can think of the same work done. Okay, work done is expanding boundary, interacting with the surrounding. You cannot put just single direction, but anyway, for convenience, I put W1, 2. But here you can see the expansion everywhere, so W1, 2 is something like a totality of this radial expansion. I can make a expand when radially. Okay, radially. Something like this. See, this is what I just put as W1, 2. Okay. And later I will look into the next slide. So no matter the actual is in the expansion is W1 to here, for the sign convention point of view, we have to put W1 to in this way. So the actual case is outward. So here if we take W1 to this way, the value can be negative. Okay, but we will put this way. W1. Oh, okay, a negative value. Same way here, W12. So you have put this way because towards the system. Okay, towards the system. Then you can see here in a closed system, M, mass, no change. Okay, volume expands, means volume change. Of course, pressure, there can be differences. Okay, so P1, P2, V1, V2, T1, T2, M1, M2. Here, this case, M1 is M2 because it's a closed system. Okay, M at 1 is equal to M at 2. So let me add this because it's a closed system. Mass at state 1 is equal to mass. I think you know the meaning of at state 2. Okay, M at state 2 is equal to M at state 1. So we can write this as M1 is equal to M2 is equal to M. That is okay. So 1 and 2 you can put as suffixes. Okay, 1 and 2 you can put as suffixes. Now the participation is 40 plus. Okay, suffixes. So this is okay. Yeah. So because it's a closed system, here you can see two cases. Okay, two cases. Balloon example and here. Okay, so from the balloon example, you are receiving heat, of course. From the sun. Okay, very long period of time. Very long period of time. That's a type of this star sign here. So it's a kind of fire. Of course, there is no flame, nothing, but the balloon is getting heated up. So we can think in that way. No harm, no harm. So don't think too much about this. So this is a very ideal case, very ideal case. So in the balloon, you see a fire-like thing, same as a power stroke of an engine. So power stroke of an engine, I think you all know, and if you have no exposure on power strokes, you can look into videos or websites or whatever. Even in the notes, you can see what power stroke of a piston cylinder system makes. Because the stroke, the movement of the one direction movement of the piston, which produces power, a huge power, a force, huge force with the displacement, we call it the power stroke. Okay, because even in four strokes, power strokes are one of the four strokes. Okay, even in two-stroke engines, power stroke is one of the two strokes. So four strokes doesn't mean all the four strokes produce power, no such thing. Because in this art of mechanism or the power generating or the art of this engine delivering work, this arrangement, only one stroke produce useful power. Okay, only one stroke. That is we call the power stroke here. Whether you know it, that should be all right. So, not like our times. Our times there were very less bikes. Bikes are now very common. Bikes are very common. Yeah. Motorbikes, I mean. Okay. So I have to look into the next slide. Okay, next slide. Sorry. I have to look into another slide here. Let's say I'm going to rearrange this. Put the balloon here. The general arrangement. It's like this. Okay. This goes here. Sorry. Yes. So where is the sun? I had one place the sun, but I cannot see that. Sun. It's here. Yes. So engine, the fire. A little bit big. Let me put it. Okay. Yeah. Okay. Good. So W12 here. I think one slide is missing. Somehow one slide looks deleted mistakenly. Yeah? One slide looks deleted mistakenly. Because the standard way is W12 I draw like this. Standard. Receiving by the system. Okay. W12 receiving by the system. So your sign may be minus or whatever, but the direction is always received by the system, work and energy. It's this. Okay. So the same way here, I put W12 like this. Okay. W12 like this. So that's why you can see generally for closed system, whether it's a well-crafted solution like power stroke of a piston or like this balloon example, you can see a similarity when it comes to the heat and work evaluation in this model. Yeah. So you can see there is one slide really missing. Never mind. Let me continue this. So M1 is M2. Can you remember? M1 is M2. M1 is M2 and the mass at the state 1. I explain it very well, but somehow the slide is missing. Is equal to the mass at the state 2 because of this closed system for both the cases. Okay, so PVT can be changed, and same way I put one more here, the internal energy. Okay, the internal energy. The internal energy, U. U. Okay. The best to have for this case, a big U for the system. Small u means for 1 kg. Okay, same way big V, a big U. Mass is okay, smaller. Yeah, okay. Big U. So I will put a big U here. The internal energy, big U. And here also a big U. So at state 1 it is U1, state 2 it is U2, general state it is U. That is okay. So if you look into energy balance now, you are very familiar with this. Energy balance. Yeah, how you can write the energy balance. Q12 Q12 it input plus watt equals delta watt. Okay, delta. Yes. So Q plus W. W here is W12. From state 1 to state 2 is delta watt for the closed system. You know that. It's the rising of the internal energy levels. Is delta U. That is U2 minus U1. Okay. That is U2 minus U1. And we know this very well now. So I just put one engineering model about the power stroke for this balloon example. I just add this. Okay. So this is the energy balance, conservation of energy. Mass balance is the conservation of mass. Mass cannot be destroyed, cannot be created here for these cases, unlike it's related to some nuclear reactions. So here mass conservation, M1 is M2. Energy conservation, energy and work together combined. So this is the case. Q12 plus W12 is the delta U, means internal energy rise. That is U2 minus U1. Okay, very good. And you know, for constant volume systems, W is 0. You have learned this. Huh? Yeah. If you can remember, you know that. Constant volume system, W is 0. So Q is delta U, that is CV delta T. So I can system, constant volume system. You have learned this, okay? So this is a reminder only. Okay, it's a reminder only. It's okay to get reminded once in a while, even though you have learned this. Here W12 is 0, okay, for constant volume system. W12 is 0. 0. So you can take W12 out. Then you know that when you take W12 out, okay, so Q12 is delta U, that is U2 minus U1. And you have another one for this case. We have learned equals Cp, so big Cp here, T2 temperature minus T1 constant volume specific heat. So this right away. Okay, Cp delta T we call this. Cp times delta T. So one more equation is here. Delta U equals Cp delta T. So this is the one you came across. For a unit mass, you can, for unit mass, this is for constant mass. So, sorry, constant mass in the sense this is for the closed system, unit masses. For unit mass, delta U is Cp delta T again, but you can see this delta U is a smaller U, C is a smaller c, then we call that specific. Okay. So I hope you can remember this. Okay. I hope you can remember this. And then I will move back to the previous slide here. Okay. I will move back to the previous slide. And going for a little bit, how to say, I need to look for some space here. So what shall I do is, take this way. Same way. Am I sharing? Yeah, I'm sharing. Okay. Balloon example. So I take this. this one. Two cases. Side by side. Okay, two cases side by side. Just leave it here, the text. Okay, good. Now, let's say we need to think of the expansion here as we need to think of the expansion. Let's say this way. Okay, let's say this way. So you can say here, when we think of same like the previous one, you have learned this pressure and volume diagrams. Okay, to evaluate the work done, I'm going to add the same PV pressure and the volume. Here the addition is an engine. Okay, the pressure and volume. So of course initially state 1, you know, state 1 pressure is quite high. Okay, pressure is quite high and volume is little small. Okay, so I'll just put this way. State 2 comes here. Pressure is quite low. Volume has expansions. Okay, pressure is low here. Here pressure is high. So the general state is, if you need, it is somewhere in between state S. Okay, that's how it is. Let me take more space here. State 1, state 2, state 3, somewhere in this PV diagram we can mark the points. So I'll mark it here. Here. Okay. Like this. So if I draw this PV, if I draw this PV, starting from 1, I will start from 1. General state S, I can take one more general state. Two is here. Good. I will make it more visible. I will put red in color, and the style I put this way. Understand? So this PV diagrams. You can see that when it comes to the consideration of expansions, probably PV diagram is important. Okay, expansion and the evaluation of the work done. The same way, if we think of the balloon, see what happens to the balloon. The other way, because in our example, the way we took it, one is somewhere here. Okay, one is somewhere here. Two is somewhere here. Sorry, S, and this is state 2 probably. And this graph is completely different now. Okay, so here you can see if I draw the same, I put this bit here. Yeah. So if I draw this, starting from one more general state, one more general state, another one, and state 2. Okay, like this. Line color I will put red, line style I will put continuous. I will put it continuous. Engine can be a faster process, and you can consider it as an irreversible, but the balloon example may be quite slow, and you may consider it as a reversible process. So you can see the contrast here depends on the situations. PV for balloon is the right side curve. For the piston cylinder system, for work done expansion, it's the left side curve. So you can see Q12 and W12, and still your equation can be the same general equation. Q12 is plus W12 is delta U. So your mass balance and energy balance, you can say this is a very good slide. Okay, this is a very good slide. I hope you can understand this very well. So, any questions before moving forward? Any questions before moving forward? Yeah. When you think about this graph, when you think about these graphs, always try to relate this to the physical phenomena or physically what's happening. So, which means in this case, if you are thinking of this, you have to have this imagination. Okay, yeah. Then you have the connectivity for the applications. If you think of the right side curve, you have to think of this imagination. Okay, this is very important. Always link it with the practical application. Yeah, of course, when you need to do the calculations, it is different. But when you think about the behaviors of pressure and volumes, whatever, when you are plotting it, it is very important to relate this to practical aspects. Understand? Good. And let me duplicate this. So we are learning more and more today. Okay. These curves, the way the pattern is, so example, if this is about x and y axis, same way here you have p and v axis. Okay. So before this, before coming to this, let me look into this as only isolated graph. Okay, only isolated graph, and your PV axis is this. Okay, this is your P and V axis. I just put this aside. Okay, you are familiar with XY. You are familiar with XY. So I'm just trying to make these two connected. Okay, you're familiar with XY. So let me take, instead of PV, it's okay me to take Y and X. Okay, Y and X. I just put, that's all. So same like PV. So state 1. So state 1 I will put X1, Y1. Coordinates. Okay. State 2 is XY. So you're familiar with this. X2, Y2, X2, Y2. So X2, Y2. State S is the general point. You always consider this as XY. Okay? And you know what X and what Y means. Okay, what X and what Y means. So make it more clear here. Yeah. So if you think of the projections on the x-axis of this xy point, the projection. We call it projection. Yeah. Let's see. Let me take a dash line. This projection value is the value x in this xy. So I just take this x on. So this is x. So I can take the bracket out. So you know about this in your O levels, A levels. You should know this. Same way, if you think of the projections, because even for some students this may be issues, so I have to make it clarify. So here now, for the y-axis projection, it is y. So combining xy, we put this point as xy. So when you see xy, you should understand it's about the separate x and y, either parameters you can mention or the variables x and y. Okay, so you should have a very good sense and familiarity of this. You should have a very good sense and familiarity of this. So you know that this is x2 here. Obviously this is the final point. Okay. This is the final point. X2. Okay. Same way, if you think of the y coordinate, sorry, x and y coordinates, the y value, you cannot say y coordinate, that is wrong, wrong terminology. So projection on y, the final point, that is y2. Okay, same way, you can think of the beginning, the starting point, that is x1. This is your projection. Okay, x1. Same way, projection on the y-axis, it is y1. y1. So this graph is the graph of variation of y with x. Okay, and the relevance is only from 1 to 2. 1 to 2. So this state, I will say this state is 1. Okay, I will say this state is 1. So you have to have this mind map. Okay, this state is 2. Okay, and if you need a general state, let's say this is S, that is all right. So what's happened? Yeah, this state is S. Okay, yeah. So now you should feel a sense that if you talk about anything, let's say 1 to 2, anything, let's say 1 to 2, you know the relevancy of the piece of graph here. So 1 to 2, okay, 1 to 2. 1 to 2 means this graph, okay, 1 to 2. This is 1 to 2. The segment of the graph from 1 to 2. This is 1 to 2. Okay. Q1 to, you can see what 1 to 2 means. Okay. Quite interesting. Okay, so you have to have this complete understanding. If you think of 2, the same way you should know what this 2 means. It is this point. Okay. So if you need 1, again you can see the point 1 here. So let me take it. I will write the same equation here. Okay. This is your 1. See, 1. So 1 means, again, this is the point. One. Okay. So you should have this very good sense on this. Okay. And this line, you can have an equation for this. Okay, you can have an equation for this. Okay, equation. So for this line, you can have an equation. So we can say that, let's see now, Q12 is okay. Q12 is okay. So where should I write? The equation, the connection between y and x. You are writing y is equal to an expression of x. We call functions function of x. Maybe you know these things very well, but I'm going to connect this because some technology students. So this is the equation. Okay, this is the equation. This is the equation. Okay, so this is going to be the equation. Okay, equation of this. What is this? Equation. Okay, equation. Or y and x relationship. So me do this way. So many arrows running around. So no choice. This is like crossing. This way may be better. Okay. So this is we call the equation, or a function of xy. Function of x explaining the variation of y against x or with x. Okay, so this is the y equals fx. Okay, the same way I am coming to this PV. Okay, P is a function of V because this is a PV graph. This is XY graph. You can say XY graph or variation of Y with X. So this is function of V. Okay, explaining the variation of P against X. Or you can say simply explaining the relationship between P and X. Okay, and X. So this is about P and V, P and V, P and V, P and V. So for P and V, now I'm going to write an expression for P and V. Again, from 1 to 2, you can see 1, 2. The state 1 is this. State 2 is this. And whatever the expressions here relevant between 1 and 2. Okay. So your Q1, 2, you have the relevancy for this. So 1 and 2 you go. Okay. So basically, I believe this is understandable. And here, especially for this PV graph, okay, I'm talking about this. P equals FV can be in the form, okay, can be in the form of, but you know the polynomials, can be in the form of P equals, sorry, let's say PV to the power n is a constant. V to the power n. Okay, so this is the general form you can consider based on some practical trends. Based on some practical trends. P times V to the power n is a constant. So this happened to be the y equals fx for PV curve, that is P equals Fv. Okay, you can write it as P times V to the power n equals constant. Okay, or you can say equals C. Okay, and C is a constant. C is a constant. C is a constant. Okay, so I believe this is okay with you before proceeding further. Okay, because this background familiarity is important when you evaluate whatever. Okay, so when I write an expression considering this, quite interesting. This is for this PV curve. Okay, this is for this PV curve. You can write it. So many things in one PowerPoint. To better, I will take a duplicate. Yeah, better I will take a duplicate of this. This is X2. I will copy this. Okay. So for this case, you can write P1 V1 to the power n. Okay. Equals C. Okay, 1. This 1. For state 1, so I will write it as subscript. Because PV to the power n is C, that's why. So P2, sorry. For state 2 also this applies. V2 to the power n is C. Okay. C. So what is this PV? This is your general V value. This is your general P value. And for any general PV values, PV to the power n is a constant. So that is the equation. So P V to the power n is a constant. So this is the curve. This is the curve. Okay. As an expression or as a relationship between P and V. Okay, for general PV. So you can write it in this way. So let me make it like this. Looks better maybe. This is the curve. PV to the power n equals constant. Or that is P equals function of V.
ඔටි දියගො
Pabutala. PVN equals C. Yeah. So before proceeding further, okay, before proceeding further, are you okay with this piece of knowledge? So for this PV in this slide, for the engine example, you have PV to the power n equals C. And also for the balloon example, you have PV to the power n equals C as well. But those C's can be different. So C can be different and N also can be different. So balloon examples N and C are different from the engine examples N and C. Okay. So now I just use this PV N equals C here. So balloon example, different N and C compared to the engine example or the power stroke of this piston cylinder. So let's say piston cylinder N and C are different from balloon example N and C. So that is the point. So I'm going to put that as a note here. So let's see. Where should I put this? Here maybe. PV equals N equals C. PV to the power N. N and C. N balloon and power stroke or the piston cylinder, let's say engine. Engine are different. N and C values. Okay. In balloon and engine are different. Are different from one to another. So what I will do is I will copy this slide and I will bring this slide here. I take this out because we are talking about N and C now are different from one another. So that is the fact. Because balloon example N and C can never be same as the engine example because engine, the function, the spark, the power reduction, the expansion, the pressure reduction and the expansion. In the balloon, the heat, somehow like spark can be from the sun, and pressure increase and volume increase together. See the difference. Pressure and volume both are increasing in balloon example, but in power stroke example, piston cylinder, pressure is decreasing, volume is increasing. In both the cases, volume increases, that's the point. For work done, there should be expansion of the system boundary, or there should be expansion of the system volume. So that is the point. Okay, so this is a good piece of knowledge, a very basic knowledge that you should have before moving forward, because without this familiarity, if you are going for equations, you cannot understand from where these equations are coming. Okay, now you have some familiarity, so generally you can have this kind of application in this way. Okay, so that's how it is. PV to the power n is a constant. Okay, I believe this is okay for you, and let me move forward. And පුතා any question? ඔකට තේරෙනවද මම මේ කියන ඒවා? පුතාලට තේරෙනවද කියන ඒවා? ඈ? කියන්න බලන්න. Can you understand this? At least you can text yes. If you cannot say yes, you can text yes. So these are very clear explanations, quite clear explanations. P and V relationships. If I add a little more, this P and V, you should know this. Same like in the first case. Okay, same as in the first case. It's there, it's mentioned there. P and V. Okay, and this is for the other case here. Your P value and your V value. Okay, P and V values are like this. Okay, remove this to see it very well. So your PVN is here. Okay, PV to the power n equals constant is about the relationship between this P and. Okay, I believe you can understand this very well. Okay, good. Any questions? So N and C makes the curves different. Okay, because N and C make the curves different. Change. Okay, N and C makes the curves different. Understand? පුතාලා තේරුණාද කියපු එක? So are you okay? Are you okay with this? Okay? Yeah. I believe it's okay. And this N, there is a name. Okay? That's the name for N. For engine cases. Okay? Engine cases we call N is polytropic index. Okay? N is polytropic index. Later I will explain why this is called that. And C is called polytropic constant. Okay? Polytropic constant. Let me duplicate the slide first. Okay? C is called polytropic constant. Polytropic index, polytropic constant. Okay? Polytropic index and polytropic constant. And this process of expansion here we call polytropic expansion or process, polytropic process. Yeah. So that is for the engine side, even that is okay for the balloon as well, polytropic. Okay, polytropic. So later we will look into what polytropic means. Yeah. It is related to this somehow. If The relationship is in PV to the power n form equals constant form. If this is the way this expands, we call this polytropic process. So let me do this way. It's a polytropic process. Give me a second, Buddha. Give me a second. Yeah, Buddha. So PV to the power n equals constant. We call polytropic process. Okay, so n is the polytropic index. C is the polytropic constant. Today, I don't think it's too much for you, but this connectivity is important. Okay, yeah, it's okay. It's okay. And you can always refer to your notes. And I'm mentioning always these are supplementary. This is supplementary. And polytropic process. So there are special situations when here you are considering only n equals, let's say 1, okay, when n equals 1. So n equals 1, you can say that PV to the power n equals C becomes what? PV equals constant. I think in grade 10, you have learned this, maybe even for physics. So what is PV equals constant? You may heard about Boyle's law, okay, that at constant temperature for a given mass at a constant temperature, okay, pressure is inversely proportional to volume. Or this is Boyle's law, okay, Boyle's law. And this is Boyle's law is a constant pressure process, sorry, constant temperature. Constant temperature process. The best word for that now, since you are universities, we call isothermal. Okay, isothermal. Iso constant thermal temperature, isothermal process. Okay, so when N is 1. So this is a very special process. Okay, this is a very special process. Understand? I believe so. So I put this over the previous text to have little memory on this. Okay, to have little memory on this. Yes, this is better. Okay, and you know that these isothermal processes are relevant only for gases. Okay, not for liquid. Relevant only for the gases. So when the working fluid is gas, working fluids. Working fluid means inside the balloon air receiving heat from the sun. In the balloon example, air getting expanded. System boundary expands. Expansion is there. So work done is there. Work done means it's a working fluid. Okay. So maybe towards the system or outwards the system. That is okay. Outwards means to the surrounding, towards the surrounding. So piston cylinder also the same. Inside, in the petrol engines, diesel engines, once fired inside from spark or from the pressure, raising the temperature high, all becomes, no more liquid droplets, but all becomes gas. Gas expands. Okay, so this is one. So when there's another special case, N is gamma. N is gamma. We call it N is gamma. For the symbol. N is gamma. I think that is not very clear here, but let me take gamma from 1. When N equals gamma, gamma means the ratio between Cp by Cv, okay, we call isentropic process, constant entropy process. Okay, that is the best work done by the system is in constant entropy process. Least work done by the system is constant temperature process. Later you can learn that. The other way for the compressors, constant temperature, compression, you need minimum work. Isentropic compressions, yeah, you have more work compared to isothermal. Okay, so two cases. How about C? Yeah, depends on the C, because the compression process, you have many compression processes, even isothermal processes, you have many. Let's say N equals 1 constant temperature. Let's say temperature is 30 degrees. You have one curve. Let's say temperature is 50. Your curve is different. Your temperature is 90. Your curve is different. The temperature is 200. Another curve. That's why C is there. For different C values, different temperatures. But PV is constant. So initial PV value, but different temperatures, your curves can be different. That's why differences. Okay. Same way for isentropic also. Based on different C values, you can see different, but all isentropic processes. Okay, but all are isentropic processes. So this is quite good knowledge for you. And I believe you may have a good understanding of this as well. So, okay, good. So, that's how it is. So, nice discussions. See, today discussion over. So, you are receiving somewhat very strong knowledge, okay, from your balloon example. Yeah. Very strong knowledge. Yeah. So, let me move forward. Okay, let me move forward with this. You have learned all the cyclic processes, energy balances, also the work done. So 1 to 5, you know that 1, 2, 3, 4, 5, 6, 7. So 1 to 7 process. It's come like this, cyclic process. Evaluating 1 to 5 as segments, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Yes, pressure times expansion. So you have recognized or you have understand the pressure and the expansion levels last week sessions. Now we can see only 38 students. Now, last week sessions. So pressure times expansion. So we have learned this. So for small segment, delta V, expansion at pressure P. P times delta V becomes the area of this strip. we came to know this, it's this. Okay. So last week explanation of this one. And with today's explanations, we are moving forward. Yeah. So total work done means the total area of strips, or total, the summation or the total of the pressure times the delta V for different P and delta V segments. Why this? 5 is 5. Okay. Delta V segments. You have learned this. So summations of P times delta V, all the strips you can see from 1 to 2. That's why 1 and 2 states important now. So left side is for the balloon, right side it's for engine. Okay, left side for balloon, right side for engines. Power stroke of piston cylinder. So same way for different pressures, little strips of expansions. So P times delta V, you add all together. Okay, P times delta V, these strips, you are adding all together. Okay, here you can see when the delta V is smaller, okay, when delta V is smaller, you can say that the limit of delta V is 0. So sigma delta V can be written as an integration of d P times dV. Okay, sigma delta W can be written as integration dW state 1 to state 1 to 2. Okay, state 1 to state 2. I hope you can remember it. State 1 to state 2. State 1, state 2. This is your state 2. This is your state 1. Okay. This is your state 2. So 1 to 2. Okay. So sigma delta V from 1 to 2. Okay, sigma delta W from 1 to 2. Okay, from 1 to 2. Here. One to 2. This is 2. State 2. State 2. Okay. That's how it is. The integration. Finally, you can see the sum of all the strips means integration P times dV. Okay, P dV integration is the work done. 1 to 2. The curve. So the area under the curve as an integration. Okay, as an integration. So for N for polytropics, N is polytropic index. So N Cp by Cv is for isentropic process. N equals 1 for isothermal process. So C is the polytropic constant. Okay. So that's all for today, Budal. I hope you can understand this part very well. We have done today. Because for separate work done under PV curves, work done under PV curves, work done under PV curves. So we will start from a new session. A new session. So today only 37 students are here. So including myself. Okay. So today attendance looks not very good because manufacturing and mechatronics. So let me continue this PV evaluation, means this slide. So let me continue in a new session so that you can absorb this very well. Okay. So that's all for today's session. So after learning this integration of PV diagrams, your closed system evaluations, you will be reaching a very good levels. And steady flow energy equations, you have the basic knowledge. So with this too, we are ready to move forward into practical applications. Example like power plants, like refrigeration systems, like gas power cycles, like vapor power cycles, about the diesel petrol engines, how the PV curves are there, how the entropy variations, we are going to talk about those. So before talking about those, some practical aspects are here. And also we will look into some closed system energy balance related questions as well. So can you remember the tutorial 1? Please, you have to submit it. You have to submit it. Now you have to submit it online. No choice. So let me create a Google Classroom for you. I think we have not created a classroom. And I will put that as assignment with a timeline so that you must submit that. Okay, you must submit that. So we will go with the Google Classroom as well as with Zoom together. And you have your own text with everyone. So you should be strong enough with the text and with the notes and with these discussions to understand thermodynamics very well in meaningful ways. Okay, meaningful ways. Because these are subjects that have more practical sense. Okay, even though you are learning some this kind of theories, these are applicable in many usages. So you have to take note on that. So you are learning something, a real subject, yeah, with real world applications, and try to understand this very well in the simplest terms, in the simplest forms. Okay, that is very important. පුළුවන් තරම් සරල විදිහට මේ දැනුම තමන් ළඟ තියාගන්න ඕනේ. That's why even I'm trying to make it simpler, not only for you to understand, but I have to make sure that your knowledge should be simple. Your knowledge should not be complicated. Complicated knowledge means this knowledge has some issues. තේරුණානේ? දැනුම කියන එක හරියට සරල වෙන්න ඕනේ. තේරුණානේ? දැනුම කියන එක හරියට සරල වෙන්න ඕනේ. Right. Okay, Bhutala, then that's all. So see you next week. Any questions? Any questions? Any questions? Okay, Bhutala, then bye for now.